So we are here with this question, sort an arrays of zeros, ones and twos. Now the problem statement is quite simple. It just says that, okay, given an array ARR containing only three values, zeros, ones and twos, we need to sort this array in ascending order. That means, seeing the sample test case, we have all these values cluttered up. We need to make all the zeros on the one side, then all the ones, and then all the twos. We simply need to sort this array. Okay. Similarly, we can see the same example here. We have three type of values. We have zeros, we have ones, we have twos. We need to sort these out. So this might seem very simple to you that we just need to perform sorting, but the straightforward sorting this array up is not the actually thing which is wanted by the question. Okay, so let's go ahead and try to discuss the approaches for this one. The very first approach, well, almost everyone is thinking of just using the dot sort operation. Now the thing is, this will get your work done very easily. You will get your work done, but what is the time complexity behind it? Well, for that it would be taking order of n log n time complexity. Now the question specifically mentions that, okay, the array has only three values, zeros, ones and twos. Why are we not making any use of this information? Because if such information is given, that means we need to go and we need to think in that direction so that we can achieve an optimal solution, right? This n log n is going to be too much for this particular question. So we need to improve our approach here, and we need to make use of this fact that only three values are present in it. So just by this observation, we go at our second approach. Okay, the second approach says that assume you have this array with you. Okay, assume this is a sample array. What do we need to do is we can count the number of zeros, the number of ones, and then the number of twos. Let's suppose we have three counters, C1, C2, and C3. We try to traverse our array from this point till the end. We encountered 0. Okay, let's increase this count. Okay, C1 corresponding to the count of 0, C2 corresponding to the count of 1, and C3 corresponding to the count of 2. Okay, we again found 0. Let's increase the count. We found 1. Let's increase this count. We found 2. I increase this 1. I again found one more 2. I increased this 1. I found 1. I increased this count. And then I found 0. I increased this 1. Then I again found 1. That means C2 is to be increased. So what are the eventual values that I have? I have C1 as 3, C2 as 3, and C3 as 2. What I have done so far? I have traversed my array once completely, okay, from from 0 to n minus 1, and I have calculated this. Now nextly what I can do is I can again go on iterating in my array, and this time I would simply fill up the values. How? Well, let's first exhaust C1. So for C1 times, I need to fill 0 in this array. That means 3 times I need to fill zeros. Then for C2 times, that means 3 times I need to fill 1. That I would do. And then for C3 times, I need to fill 2. That means 2 times I need to fill 2. So this approach led us with this answer. Is this answer right? Yes, it is. Is this approach correct? Yes, it is. But what are we doing here? We are iterating this complete array 2 times. Okay, first iteration is to calculate the counts, and the next iteration is to place the values. Now this leads to like order of n only, but still we know that we are taking 2 iterations of it. Are we using any extra space? Well, we can say, okay, we are not using any extra space here. It's order of 1 only. Okay, the space-time complexity is order of 1. Now, although this is a very good approach, but there exists a better approach. But before that, let's discuss the code for this one. So the code of this problem is really simple. We have taken 3 variables, and this time the code has taken C2, C0, C1, and C2. C0 for 0, C1 for 1s, and C2 for 2s. Quite simple. And then what are we doing? We are simply iterating in our array. We are iterating in our array. We are saying that whenever I encounter 0, increase this counter. Whenever I'm encountering 1, I'm going to increase C1, and otherwise I will increase C2. Once this iteration is completely done, I would have all of these 3 counts, and then I would just take up one index and I would fill all of these values. For C0 times, I'd be filling 0. For C1 times, I'd be filling 1. And for C2 times, I'd be filling 2. Now we know that this code can work, but it is not that optimal. We need to make it a little more optimal, right? So for that, we are now going to see another approach, which is going to be the most optimal one. So for this third approach, we will be taking help of DNF algorithm. Okay, DNF algorithm is a very famous algorithm, and DNF stands here for Dutch national flag, and we will be finding soon that why it is called so. Okay, so you need to assume that you have three types of colored balls. You have red colored balls, you have white colored balls, and you have blue colored balls. Okay, arrange in a linear fashion like this. Now your task is to rearrange all of these so that you have groups of red, white, and blue. Now also we have a restriction that we only need to take one pass of this arrangement. We cannot come back and we cannot juggle. We just need to take one pass from this end till this end, and the three partitions of my array should be made. Now this is the problem statement. So for this, what do we have to do is we have to divide our array into a few parts. The first part would be containing all of the red balls. Then the next part would be containing all of the white balls. Then I would have this portion, which would signify, or which would have my unsorted balls, which means these are still need to be placed in the respective positions. These are still what we are working on. Okay. And then the last part is the blue balls part. Now, what do we do here? Every time from this portion, the unsolved portion, pick up a ball and we see what is the suitable position for this one. We picked up this one. We saw, okay, it is blue. That means it is need to be kept in this part. Once that is done, we would encounter another ball, which is white. The correct position for this is this part, right? We would place it in like in this particular part of our array. And then the red ball would go here at its respective chunk, and then again white would again go here. Once this is done, that means this unsorted, or you can say unsolved part is over. We would be left with three parts in this array, and those three parts are going to be the red balls part, the white balls part, and the blue balls part. And just because this symbolizes like the Dutch flag, this algorithm is named after that, and it is called as Dutch national flag algorithm. Okay, now this is to linearly sort three objects. And in our question, we are doing something very similar, right? We have these elements. We have three elements. We have zeros, we have ones, and we have twos. We are going to make this, we are going to implement this algorithm now. Okay, how are we going to do that in our question? Let's take this example for it. Assuming I am in the middle of solving my complete problem statement, complete array, and such that I have my array divided into three portions. The first one is this one. That means from the beginning till low, I have one portion, and the other portion is from low till my another pointer mid. Okay, and then the third portion is high, from high till the end. Okay, which would have my twos. Now between middle and high, this portion is the unsolved portion. Unsolved portion. So every time we are picking up a value, we are picking that up from the unsolved part, and we are trying to place that at its particular location wheresoever it is needed to go. How are we going to do that? Let's see. I have to always focus upon the middle value that I have. So at middle, I have 2. Well, what is the correct position for 2? We know that after high is the correct position for 2. So now I need to perform a swap between mid and high. So once I perform swap between mid and high, that means this goes here and this goes here. I would have this 2 as here and this 0 as here. Now that I have added one more to my high would decrease. You can say move in this direction once. So I would take my high from here and I would move it here. Now that you can see the middle value that I hold is 0. And where does 0 go? 0 go here, before low. So for that, I need to swap this low with this mid variable that I have. So here, once we swap like this one goes here, this one goes there. The values will be 0 is here and 1 comes here. After swapping the 0, now I know that which place I have actually increased the count of. That means, okay, 0's portion is increasing. I need to move my low pointer. Okay, because I have done one fixing, I also need to move my mid pointer to go ahead to a new element. Okay, so this goes like this. My mid pointer would also move here. Now that my mid is here, again I have to choose. Okay, I have to see what is happening here. What element is it? It's 1. Where does 1 go? Well, 1 is actually at its correct position if we just move it one step here, right? So for that, in this condition, once we have 1 at the mid, we would just increase the mid. Okay, we would just increase the mid, and that would make 1 fall in its respective position. Now again, I have 0 at mid. What do? I've already increased my low once here. Okay, make sure of that. So yeah, once my low is at its correct position here and I mid it at this position, I would do the swapping here and here. So once the values are swapped, a 0 will come here and my 1 will go there. So after these many swappings, you can see what has happened. After this one, my mid would move for one more time. It would go here. It would check that, okay, it is also 1. That means I need to move ahead. Once I move ahead, my mid would go here. Now here I can see I'm having a clash. If and also my mid value is 2. Even if I want to swap, that value would be swapped with itself, and high would move one step on this side. Here I would encounter a situation where my highest value is getting lesser than my mid. This is where I have to stop. That means my middle portion is exhausted. My middle portion or the unsolved portion is exhausted, and which actually leads me to the answer that the complete array that I was having is now sorted, as you can see in this example. So this was just to explain you, because like I've taken this array and I have taken up a middle step of this complete approach so that you can understand better how these 2 pointers or these 3 pointers are working. Now let's see one example in which we are dealing with the complete array from the initial point till we sort it out. Okay, so that you can have a very clear understanding of Dutch national flag algorithm. Let's just start with this one. So assume this is the array. Initially, my low and mid are both going to be at the first element, and my high is going to be on the last element. Now, what we do, we've already seen that if my mid has 0, we swap. We swap the low with the mid, correct? And we increase low and mid. That is what we do. So here you can see I have my mid as 0. So I would swap low and middle. Well, this would not affect much because that we are on the same element. And then we have to increase both of these pointers. That is what we have done here. Now I can see I'm getting 1 at my mid. So this point, if my mid is equal to 1, then what do? I do not swap anything because I am actually like very near to the position I have to place 1 at, just 1 back. So I would instead of doing anything else, I would just increase my mid by 1. So I would do mid plus equals 1. That's all. That is what we have done here. Now my mid has 2. What do we do once my mid is 2? Again swap. But this time I swap mid with high. And because I'm increasing the portion of high, I would decrease high's value by 1 so that we can move our high pointer in this direction from right to left once. Okay, this is what we have done. We have swapped the values and I have increased it once. Now you can see after the swap is done and after high has moved, my mid still has the value 2 because that is how it was that is what we got after the swapping. Now what do we need to do? We again need to perform the swap. I would again perform the swap, and this time you can see the values are fixed correctly. Okay, and I have moved my high as well. So once this is done, again my mid is having 1 as its 1 as the element. What do we do once we have 1? We just move our mid. So once I move my mid, I would have this situation. Once I have 0 at my mid, I swap low and the mid. So these two values would be swapped, and you can see after the swapping, I have my high here and my mid here. That means my highest value is now less than my mid's value. This is the breaking point. We know that if this has happened, that means my array is sorted. Okay, let's quickly see the code for this approach as well. The code is quite simple, just what we have discussed in the diagrams, completely the same. We have n keeping the track of length of the array. Then we have 3 pointers, low, high, and mid. Low initially at 0, high initially at the last element n minus 1, mid at 0 as well. And then while mid is less than equal to high, at till that point I'm going to keep on moving. I will check if my value is 0. If the middle value is 0, then I would perform the swap between low and mid here, and I would increase my low and the middle by 1 step. Otherwise, if my mid is 1, I would simply increase my mid by 1 step. And if that is not the case, that means we have 2. For that, I would perform the swapping between the middle and the high element here, and I would decrease my high. That means I am moving 1 step in the reverse direction. So once this loop is successfully executed, okay, and this condition is reached, this loop would break and my complete array would be sorted that I can return later. Now, what is the best thing about this approach? How many times are we traversing this array? we are just traversing this array for once, making its complexity to be order of n. And we are also not taking any extra space for this algorithm, because the space complexity is going to be order of 1. So this property actually makes this particular question be solved with this optimal approach, the DNF algorithm. Okay, now let's test the code against the test cases. So here's the code. Let's compile and run it. All right, it's compiling fine, giving us the expected output. Let's try to submit that. Okay, so now it has passed all of the test cases successfully. I hope now you have gotten this optimal approach as well as the other approaches as well. So do solve your question now. And if you find it anywhere difficult, you can ask us in the comments. And if you like the video, then do like it and tell me in the comments. Thanks.